Okay, we want to talk more about base 10 because we've seen already that this is a very, very common base for us to use. You know, we're always talking about tens and hundreds and thousands, and of course that's a base 10 system of numbers. So we're using base 10 a lot. We use it for the Richter scale. You'll see we're going to use it for loudness as well. So all of these things are based on base 10. So this base is so common, we call it the 10 is the common base, okay? And what we do then is we allow ourselves to write a logarithm and omit the base. So if I just write log of x, whoops, I did that backwards, let me undo that, take that away. If I just write the log of x, so I have no base written, then this is assumed to be a base 10. So by definition, if there's no base written, then you can assume the base is 10. So a lot of times you will see log written without a base. And that's exactly what's happening on your calculator as well. Of course, the metric system is a perfect example of base 10 system. So let's do a little practice. You know, when you have log of 10, you could easily think of that as being 1, right? What is the exponent? What is 10 to the what is equal to 10? And I said 1. Let me ask you to evaluate log of 1,000. So you're asking yourself 10, because that's the base it's hiding, 10 to the what is equal to 1,000, and you should be telling me 3. I could also say log of 0.1. Okay, think about that one and see if you can get that answer using your common base, 10. 10 to the what is equal to 0.1. If it's helpful, you can write this as log of 1 over 10. Maybe that's helping you. Now, 10 to the what is 1 over 10. Becomes a little more obvious the answer is negative 1. So often we're using scientific notation and we're using this sort of exponents, right, for the metric system and all that good stuff. So we have our common base. And of course that is the button on your calculator. So let's see if we can find some things on the calculator. I want you to find your calculator and just punch it in, log of 7. We're going to find that on the calculator. You're going to pull it out, punch the buttons, and you should be getting something that looks like 0.845. Now this is not an exact value because I've had to round it, so I'm using the approximate symbol there to say that it is approximately 0.845. One more, let's make sure we've got this log, punch the buttons of 3. Let's do 0.3. Yeah, because it brings up this point, I just want to see if you can catch the patterns that are going on. And what do you get for that when you punch it in? You get a negative number. Okay, that's what I want you to pick up on here. 5, 2, 3. So any number that's less than 1 is giving you a negative, right, answer. And if you think about what the parent function looks like, that should make sense to you, right? The y values are negative when x is less than 1. And remember, we don't ever go logs of 0 or negative numbers. All right, so we have those. And since we have the logarithm on our calculator, we can often use those to help us solve some equations. So in the past, we would have an equation that looks like this. 3 to the x is equal to 7, right? And we would solve this this time because we know we can take a log of both sides. So what we're going to do is we're going to log both sides. So I can write log of 3 to the x is equal to a log of 7. Now convince yourself that you can do this because how many times have we done this in the past? We use that equality property where if you have the log with the same bases on both sides, you can cancel out the logs. So now we're just adding in the logs rather than going in the reverse. So this is a true statement. If this is true, then it has to be also true that the second line is true. And now that I have it written as a logarithm, I can use that real powerful, remember I liked so much the power rule that allowed me to get rid of exponents by bringing them in the front and down low. So this little exponent right here comes down in the front, multiplies times log of 3, and I still have this log of 7. And now remember I'm trying to solve for x. This was times, so I'm going to divide both sides by log 3. I have log of 7 over log of 3, and I can do that on my calculator. So I'm going to pull my calculator out, hit the buttons, and I'm going to come up with a value for this, 1.77. So that's my approximate answer. So how sweet is that, okay? Which is really cool. So I think I'll let you go ahead and try one of these for yourself. So I'm going to ask you to solve this one. What if you had 5 to the x plus 1 is all equal to 11? I'll go ahead and pause it while you solve that. Alright, and you can follow along with my solution that x is 0.49. I was just real careful to use parentheses around my exponent, okay? So I'm going to remember this. I want to come back to this right here. So I'm going to write that again on the next page. Okay, so I sort of wrote the result. I said we had this question, and I had this result by taking the log of both sides. And I was using common logs. But before that, remember what we would have done to this. We would have looked at this expression and said, well, I can write that as a logarithm using the definition. Okay, so we have these two tools. We have this, equality property, which is what we did to get this. But we also have the tool of that definition using the if and only if statement. So I'm going to use that if and only if to write this as a logarithm. But again, I have to use base 3. So log base 3 of 7 is equal to x. So I have two ways to write the answer x. One using common logs, which is a ratio of two common logs, and the other is a logarithm with a base 3. So what we've come up with is these two things must equal each other. So I've really just come up with what's called a change of base formula. If I have log base 3 of 7, that equals log of 7 divided by log of 3. And what we're going to find is that this does, what's the word? You can use this for any base in any argument. Excuse me. So what you want to remember, though, is it was interesting that the little base, anyway that's low and below the line a little bit, here you have this line that you tend to write on, right? So the base is tending to be a subscript below the line, is going to be the logarithm that is below the fraction bar line, okay? So if it was low here as a base, it's low here in the fraction, and the other number, the 7, stays high above the line, okay? So that's why you're going to remember it. So in general, you have this rule to remember. Log any base of x is equal to common log x divided by common log of what used to be a base, okay? So that's what's really odd here, is that base is now losing its position and taking on a new role. Okay, so this is what you're going to remember. It works for anything. So why don't you do a little practice? I'll give you a problem here. You try this one, and what you can do then is find the answer in your calculator, but I want you to write it out and then go to the calculator. So find the log, I don't know, base 13 of 25. How about that? Do two things for me. Write it as a ratio of two logs, and then find the value on your calculator with an approximation. I'm going to pause. Alright, so you see my answers. I got log of 25 over log of 13, punched in my calculator, and I get about 1.25 when I round that to 2 decimal places. Alright, let's spend just a minute and talk about decibels. Decibels are a unit of loudness. Okay, so when you go to a concert, there's a lot of decibels there. When you're whispering to somebody, there's not so many decibels. So it's a measure of loudness. And I don't want to get any more technical than that. We can take some physics classes and measure that better. But what's interesting to note is this is going to be a little different than the Richter scale. They're both logarithmic scales, but in this case, the bell is logarithmic, okay? And you'll notice I'm talking about decibels, but think about the decibels as being that metric deci, which means a tenth. Like a kilobell would be 1,000 bells. A decibel is a tenth of a bell. So that adds a little bit of a complication to us. It's just the way they've chosen to do this to make the numbers work out. Alright, so we have a decibel, which is a tenth of a bell, where the bell is in a logarithm. So what happens is, when you're comparing, let's say I want to compare 32 decibels, compare to 42, no, I don't want to do that, that's too complicated, to 52 decibels. Let's do that. And this can be abbreviated. Let me show you the abbreviation. For this, it's a little d and a big B. That's 32 decibels. So this is 52 little d, big B. And that's 52 decibels. So if you want to compare these two, the first thing you have to do is go to a bell, so then you can go to the logarithm. So this would be 3.2 bells compared to 5.2 bells. So now you have 10 to the 5.2 compared to 10 to the 3.2. So now we're doing the same thing we did with the Richter scale. How do you compare two of these? And you're going to get 10 to the second power. So you would say 100 times louder. Okay? So this 20, a difference of 20, is really a difference of 2, which is 10 squared, which makes it 100 times louder. So 20 decimals difference is 100 times louder. Okay, so if you remember to change to a bell, then you can more easily calculate how to compare those. All right, so we'll do some of this practice in class tomorrow.